In this video, we're going to start looking at the idea of combinatorics, specifically counting problems. So we're going to develop and apply something called the fundamental principle of counting, and we're going to talk about and introduce factorials. So first, let's introduce this idea of counting in combinatorics. So let's look at three different problems, ones that we're going to be able to answer by the end of the next few videos, and talk about what's kind of going on here. So first example says, if you went to a restaurant with 7 choices of appetizers, 12 choices for an entree, and 5 choices for dessert, how many different 3-course meals are possible? So we're trying to count the number of choices that there might be. The next one says, as a member of a snack box subscription club, someone will receive 5 different boxes representing snacks from 11 different countries. So it'd be like 1 box from each country. How many different combinations of snack boxes are possible? So in that case, there are 11 different countries to choose from, and you receive 5 of those. So how many different sets of 5 are there? And lastly, we could say, how many different podium finishes, that's first, second, third places, are possible in an 8-person 100-meter dash? So all of these are problems we're going to be able to answer. We're going to start with just one kind in this video. But we're going to do it not just by counting individually one by one, even though we could, it just would take a while. We're going to use some shortcuts. First being the fundamental principle of counting, and then we'll talk about combinations and permutations. So these counting methods, these shortcuts we're going to use to count these things, is a subsection of what we call combinatorics. Combinatorics is a much larger branch of mathematics that covers a lot of different kinds of problems, but this is just one part of it. So in this video, we're going to focus on the fundamental principle of counting, and that as a shortcut to answer one of these problems. So let's look at an example. So when picking an outfit for a day, a person chooses between 2 pairs of jeans, blue or black jeans, 4 shirts, red, green, white, and gray, and 2 pairs of shoes, athletic or casual. How many different possible outfits are there? Assuming that everything works together very well and you can mix and match in any way. So one way that we could do this is we could use a tree diagram to help look at all of the different possibilities. So we'll start with the idea of your choice for jeans, 2 pairs of jeans. You could either get blue jeans or black jeans. From that point, then after you pick your jeans, you need to pick which shirt you're going to use. And that's going to be 4 choices. So you could either have red, green, white, or gray. So from each of the jeans, the blue and the black, we can say 4 different branches going out, representing our 4 choices for our shirts. And then from each of those, we have 2 choices of shoes. So we could either have the black might be athletic, we'll call it just an A. Or we could have casual. So that's a wonky looking tree diagram. But again, what we have is we have 2 options that we start with. From there, we branch out to 4 different options. Then from there, we branch out to 2 different options for each. Each of these branches represents a different outfit. So for instance, let's look at the option corresponding to this branch. That is black jeans, red shirt, casual shoes. And each branch here represents a different outfit that we could choose. And it represents all different outfits that we could choose. And together there are 16 options. So we just counted the total number of options using a tree diagram to kind of help us look at all of that. This strategy will not always work though, because our choices might just become too large and drawing a tree diagram is just not really feasible. So we need some other kind of shortcut to help us out. And that shortcut is the fundamental principle of counting. So this says that the total number of possible outcomes of a series of decisions, our decisions might be to where, which jeans are we going to use, what shirt and what shoes, or making selections from various categories. This is found by multiplying the number of choices for each decision or category as follows. Our idea is we're going to draw a little box, maybe a blank for each decision. We'll see an example of that below. Then we're going to enter the number of choices for each decision and multiply. And this will be the exact same idea as showing us how many different branches of the tree we're going to have in our big tree diagram, except we don't have to draw huge trees. So let's look at an example of this. Our first example from the first page, if you went to a restaurant with 7 choices of appetizer, 12 choices for an entree, and 5 choices for dessert, how many different 3-course meals are possible? So first thing, we're going to draw a box or a blank for each decision. So we have our choice for appetizer, our choice for entree, and our choice for dessert. We can even do it as a box, and then we'll do a blank in the next one. So our first box represents the appetizer. Next one for the entree. And lastly for the dessert. So then we're going to enter the number of choices for each decision. So there are 7 choices for appetizer, 12 for an entree, and 5 for a dessert. And that means that the total number of meals are going to be taking those numbers and multiplying them together to get us a total answer of 420 options. So let's do it again. We're going to do the same example, but we're going to add 8 choices of beverage, 3 for salad, and 5 for soup. So here we have apps, entree, dessert, beverage, salad, soup. And we'll label this as well. So apps, we have 7 appetizers. Entree, we still have 12. Dessert, we have 5. Now we're going to bring in the idea of a beverage. We have 8. 3 choices for a salad. And 5 choices for a soup. And we're going to take these numbers and we are going to multiply them together to get us a total answer of 50,400 options, or different 5-course, 6 whatever. Yeah, 5-course meals with a beverage included. So again, a tree diagram would not be feasible in this problem. It would take way too long to draw, and then you'd have to count manually at the end. But really what we're doing, if we go back to the tree diagram example, is we're taking our options. That's showing us how many different branches we have. We start with 2 options in the first row, the first column there. Then we have 3 options each, or sorry, 4 options each. And then we have 2 options at the end. And if we take 2 times 4 times 2, we get our 16 total options. So let's look at another example. A serial number consists of 2 consonants followed by 3 non-zero digits followed by a vowel. And in this case, we're going to call vowels A, E, I, O, or U. We're not going to consider Y a vowel. So then we're going to determine how many different serial numbers are possible given the following conditions. So firstly, we're going to say that letters and digits cannot be repeated in the same serial number. So there are 6 different digits that we need to look at, 6 different things. So let's make a little box for each of those. This is part A. We have a box for our 6-digit serial number. And let's kind of label each box so we know what we're kind of doing. We start with 2 consonants. We'll just say consonants. Followed by 3 non-zero digits. Non-zero numbers. And then finally, a vowel. Now we just need to decide how many different possible options do we have for each decision. So note that there are 5 vowels, which means that there are 21 consonants. 26 minus 5 is 21 consonants. And there are 9 non-zero digits. So let's look at our options. For consonants, we have 21 options for that first consonant. And actually, let's look at part B kind of at the same time. And it's going to be the same, very similar problem. All right, so in both the problems, one, the letters and digits can be repeated, the other one, they cannot. But in either way, we have 21 options for that first digit. If the letters can be repeated, then we also have 21 options for that second digit, the second place. But if they cannot be repeated, like in part A, then we use one of the consonants, which means that we only have 20 left to choose from. So let's say we picked like a W as our consonant, right? Then we think about all 21 consonants we can choose, except we can't choose W, which means we have 20 left to choose from. So that's the difference between replacement and without replacement, or repetition and not repetition, is the numbers will change each time and go down by 1. So non-zero numbers, there are 9 non-zero numbers. And if we don't care about repeating numbers, then we just have 9 options for each of those non-zero numbers. However, if we can not repeat, then we have 9 for the first, 8 for the second, and 7 options for the third, as we get rid of one option each time. And then finally, we have a vowel at the end, which is 5 options, and that couldn't happen anywhere else before, so that's just going to be there. Then to get our answer, we multiply all of these numbers together. First one, we get 1,058,400. And in the second, 1,607,445. All right. So the other part of this video is we're going to look at factorials. So a factorial is an operation that we can do on a number. In this case, n has to be a positive integer. So n factorial, which we look at n exclamation point, is the product of all positive integers less than or equal to n. So the really mathy definition is n factorial equals n times n minus 1 times n minus 2 times n minus 3 times n minus 4, all the way down to 5 times 4 times 3 times 2 times 1. We take the number and we multiply it by the preceding number over and over and over until we get down to 1. Note that there is a special case here, and that is, what do we do for 0 factorial? And in this case, 0 factorial is not 0, but in fact it is 1. And there's a lot of reasons for that. The reason that's not going to be very satisfying, that I'll say first, is factorials are used all throughout mathematics, and having 0 factorial equal 1 keeps with patterns that happen with factorials exactly, whereas if you set it equal to 0, it does not, and it's really kind of important for that reason. The more satisfying answer is that there is a relationship that really does show why it should be 0 factorial. We'll kind of introduce that when we talk about permutations next. But in the meantime, just know that 0 factorial is defined to be 1 in a kind of a similar way as, any number to the 0th power is 1. There's kind of a similar sort of thing going on there. All right, so to get some practice with factorials, let's look at calculating some factorials. So 1 factorial is you take the number and you multiply it by its preceding number until you get down to 1, but there's nothing to do there, that's just 1. 2 factorial, you take 2 and you multiply it by its preceding number 1, and then you stop, so that's just 2. 3 factorial is 3 times 2 times 1 is going to be 6. 4 factorial, 4 times 3 times 2 times 1 is 24. And 5 factorial is 5 times 4 times 3 times 2 times 1 is 120. These numbers get really big very, very quickly. And to actually see how big they get, you can see a video online about 52 factorial. 52 factorial is special. It's the number of different ways that a deck of cards could be shuffled. 52 factorial. And there's a really good video that kind of shows how big that number is. That's done by Vsauce. So these numbers get really big really quickly. By 5, we're already up to 120, and it's going to get much bigger than that. All right, let's look at where this might be useful, this idea of factorial. Let's look at the example. 4 people go on vacation together and must decide who will sleep in which bed in an Airbnb with 4 different beds available. How many different ways can the beds be decided? Well, let's use our fundamental principle of counting. We have 4 different beds to choose from. Right, this is bed 1, bed 2, bed 3, and bed 4. So let's think about if we're, 4 people going on vacation, there's the beds. We have 4 options on who gets that first bed. We make that decision, we go on to the second bed, and we say, who is going to sleep in that bed? Well, we don't have to pick the person we've already picked for the first one, so that means that there are only 3 people left. Then we don't need to consider who is in the first and the second bed, which means you only have 2 people to pick from the third bed. And then finally, that just means that the last bed has been decided. There's only 1 person who can go in that last bed. And therefore, we have 4 times 3 times 2 times 1, which is the same as 4 factorial, or 24. This is a way that a factorial can kind of come up in these problems, and we're going to see it a lot more when we talk about permutations and combinations. All right, last, let's do some just some algebra with factorials, getting used to some of these expressions. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. But actually, another way that you could do it is you can recognize that 5 times 4 times 3 times 2 times 1 is 5 factorial. So you could write this expression as just 6 times the entire thing, 5 factorial. And that can make things a little bit easier sometimes in dealing with this algebra. Note that'll be 6 times 120, or 720. Note that a calculator will have a factorial button often, so you could be able to use a calculator for that, especially to get to big numbers. All right, let's look at dividing with some factorials. That's something we're going to do in the next couple of videos. 8 factorial over 5 factorial. Let's write this out with the definition. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 times 4 times 3 times 2 times 1, 5 factorial. And we could definitely just multiply the top and the bottom, and we can get an answer. But there's some shortcuts we can do in this calculation. Note that we can cancel out, since this is all multiplied together, we can cancel out some terms. We have a 5 on the top and the bottom, a 4 on the top and the bottom, a 3, a 2, and a 1, which means that this whole thing is just going to turn out to be 8 times 7 times 6, which will be 336. Another way to think about this calculation is doing something similar as we did in the first example. We could write 8 factorial as 8 times 7 times 6 times 5 factorial over 5 factorial. And again, instead of canceling out 5 times 4 times 3 times 2 times 1, we can just cancel out 5 factorial from the top and the bottom, and we get our same answer here, 336. All right, let's do one more. Let's look at 8 factorial over 3 factorial. Let's use some of our kind of ideas. Again, this will be writing it all out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 5 times 4 times 3 times 2 times 1, times 3 factorial, which is 3 times 2 times 1. And we can do a bunch of canceling out there. We have our 5 factorial, kind of the same thing as we did before. Then we have 8 times 7 times 6 over 3 times 2 times 1. Note that 3 times 2 is 6. We can cancel that out, and we'd be left with just 8 times 7, which would be 54. Again, we could write this as 8 times 7 times 6 times 5 factorial over 5 factorial 3 factorial. 5 factorials cancel out. 8 times 7 times 6 over 3 factorial is 3 times 2 times 1. And then we have our 3 and our 2 cancel out with the 6. And there's our 54. And we're going to do those kind of calculations a lot in the next few videos.